Maybe the computer will be going. Oh, fuck it. We'll just like talk a little bit first. Maybe. It's not mind controlled. How do you think you raised that? You ever seen such a thing? Wow, that is dramatic. Hi everyone. Hello. I'm getting back into it. Welcome to, do you know you're in real analysis? Cool. This is like one of my favorite classes to teach. So, and to work with. And we're going to do things, we're going to have to bring the syllabus back up because if you've had a class with me before, I've always had this structure where we do homework and then we have exams, and then I realize I hate exams, and then we toss out an exam, right? And we're like, oh, that's too many exams, let's not do all those. And then I'm like, let's not even do them here, they're just homework. So I kind of like did some introspection. And I thought, let's do something different. So we're gonna do a very different grading structure in here. And basically you'll have the chance to earn whatever you want. I don't even know, the syllabus is up in world class, you can check it out, I'll tell you what it is, we don't need it. So essentially I'm gonna give you about 50 homework problems this semester. By the end of the semester, you'll have the opportunity to do about 50 homework problems. How many of those you do determines your grade, and we'll also have some quizzes. So it's something like this, I think I can remember this. So there's gonna be approximately 15 homework problems. I went back and looked how many I've assigned in the past over the last couple times I've taught this and thought, it's about 50. And so anywhere from like 46 to 50, this is in the A category, and then is probably like 42 to 44 for B. You can go check out, nobody's gonna do less than this, come on, like seriously. Do I even need to put up anything lower than that? I don't think so, not with this group. We're not gonna do that shit. So we're gonna have homework, but we're also gonna have some quizzes. And the quizzes are gonna be only to help you memorize definitions. So a little bit like geometry, what we did in geometry, where we just had definition quizzes. So we'll have some of those just to help you like memorize basic results. There won't be hard problems on them. All the hard problems will be right here. And so I think here, if you get like a 90% or above, and this, you'll get an A. And then like down here, I think this was 80%, so a very classic breakdown over here. And then if you get some weird combo of these things, that's where the middle grades fall, and we'll figure out what that's gonna be. Maybe we'll talk about it. Does this all sound pretty reasonable? And then also, so the homework, I'm gonna do that differently too. I'm gonna do this thing that I got from Cyber and Patnot, because I really liked the way it sounded. And I think I talked to you about doing it last semester, mastery grading. So I'm kind of doing it a little bit differently than they are. Basically, and I'm gonna give you 3 homework problems a day. They're gonna be due next Wednesday. But what I will do is give you like, done, you understand this. Second, you don't understand this. This needs some tweaks. Or third, like, good God, what are you doing? Fix this completely. So you'll get like a 1 to a 3 or something like that. And from there, to get credit for it, you have to get it up to that mastery level. Like, I understand this, I did a good write-up, and I communicated. And you'll get 2 chances. So I'll give you the homework, and then whatever problems, I'll try to get stuff back to you as soon as possible. And then if you want to resubmit something, you have a week to resubmit it. And then I will get that back to you ASAP, and then you'll have 1 more week. If that one still's bombing, you got 1 more try. So 3 attempts on each homework problem. And my hope is that you'll just like learn better this way, right? And then I don't have to be like cop. I hate being a cop. I hate like giving people grades, and I end up giving most people A's. Let's be honest, everybody knows that. Everybody's here maybe knowing that quite well, that I'm an easy grader. So this, I thought, this would help me help you learn better and not just give you an A, make you earn the A just a little bit. Okay, cool. All right, thank you, thanks. I'm glad everybody's on board. Now I just gotta find an eraser. Here we go. So that's the basic structure of the class. There's no exams. I wouldn't have had any exams in here anyway. That's just not what we're gonna do. But what we are gonna do is study infinity. That's what I think of this class as really like getting to know infinity at the tiniest scale. First we're gonna do the tiniest scale, and then we'll take a little break where we look at the biggest scale and talk about the many kinds of infinity. But we're gonna first talk about the many kinds of smallness. And we're gonna break apart this thing that you've been using your whole life. Good God, I gotta start throwing these things already. Now I'm getting puffed up. Now I'm getting amped. You have this thing called the real number line. And honestly, that's what this class is half about. The second half of this class is about functions that take values from here and spit out new real numbers. So this is one-dimensional real analysis, and you could think of it as the behind the scenes of calculus. All the stuff that you brushed over in calculus, don't worry, you get to do it all now, like in intimate detail. You're gonna do a delta epsilon proofs, and you're gonna show that things are continuous and all sorts of goody stuff like that. This stuff is pretty new. Like, this is kind of like mid-1800s. That's when this all started happening. So this is very recent math for the most part, but also really old, right? It's at least almost a couple hundred years old at this point. But there was a point where people were doing shit and just getting weird results, and there was no standardization, and then a group of mathematicians came along and made this all rigorous. Like literally in our book. So our book is, I've never taught from this book either, this Ross Elementary Analysis. I'm sure you can find a free PDF online. If not, someone can help you. Or if you like to have the nice physical book, it's not that expensive because it's been around for a long time. Anybody not got the book yet? It's cool. Okay. Yeah, I'm pretty sure there's PDFs available online, but maybe you want a hard copy or a paperback, and seriously, like 30 bucks, you should be able to get this for like 30 bucks. I'll see if I used to have like Lou Grobart would always find my illegal PDFs for me, and then he would first see if they had viruses and then give them to me. So if you find a PDF, let me know after you scan it. What I'm gonna ask you to do, if you can, start on this ASAP. Start reading chapter 1, because I'm not gonna talk about everything in here. I'm gonna hit the stuff that's important for us. So what am I not gonna talk about? Well, mid-1800s. So we've got the real number lines, but before that, we had just some primal numbers. You know, what do you think the first numbers people came up with were? You probably had history of math, some of you. Like, what are the first numbers people thought about?
1, 2, 3, 4.
Yeah, right? And why? Why is that, Cormac?
Counting things.
Because they had to count shit, right? They had to keep track of how many rocks they had or how many potatoes were in the bin and stuff like that. Because it's just like really nice, useful numbers. And these numbers here, we kind of just take them for granted. What's a number? I'll sit down for this. What's a number? When I was hanging out with my family and things got quiet, I had this little recording of crickets that I would put on just to crack everybody up. Should I get that out? What's a number? What do you think? What do you think, Christian?
well, kind of going along with the counting thing, I was gonna like say some sort of like way to measure things, but I guess.
That sounds like a pretty reasonable thing. So it's like a symbol representing some measurement here, like a count, right? That sounds pretty good. But then the question also can have all sorts of weird, it can get very abstract. And it did in the mid-1800s. In the mid-1800s, now these are called the natural numbers, and we denote those with this kind of nice N, the natural numbers. But in the mid-1800s, people wanted to lay down the law on this and understand what is these? How, we're just saying, and this just keeps on going, whatever that means, right? This ... that's kind of a heavy philosophical thing. Just forever, never ends, whatever that means. We'll all end, these won't end. So, in the mid-1800s, a little later, like 1880s, this guy Piano came up with these axioms. And this is what I'd like you to read about in the book, because I'm not going to cover them. And our book doesn't really do them justice either. Piano came up with these 5 axioms that described this set. So this is all going back to set theory. And set theory was a mess even until the early 1900s, when people like Bertrand Russell and Whitehead were like trying to figure out, well, math ended up collapsing because of set theory in the early 1900s. Like, it's a thing people don't know about. How many of you know about this, when math broke? That math collapsed and people weren't sure it really had any meaning whatsoever. So I would say, if you're curious, look up Russell's paradox. Bertrand Russell was a humanitarian philosopher, mathematician, philosopher, the really craziest mathematicians are mathematician philosophers. They all end up losing their minds in some way or another. But Russell's paradox, I'll just kind of I guess I'm here. I might as well talk about what it is. It's the set of all sets that do not contain themselves as sets. I think it's something like that. It's some crazy statement. It's kind of akin to this. It's a self-referential set. But it kind of all comes down to a statement like this. If this is false, if the thing this is saying is false, then it must be true. If it's true, then it's telling the truth, and it's false. And just this kind of infinite looping. So this all comes down to, is anything I write mathematically meaningful? And so he spent 20 years building this thing called the Principia Mathematica. And it was supposed to be laying mathematics on firm foundation. And then, in 1920-something, this guy, Kurt Gödel, came along. And for his PhD thesis, he was kind of he was the primal computer scientist. He came up with this thing called the incompleteness theorem. And from that, as soon as Russell said that, saw that, he realized his 20 years of work were meaningless, because he basically showed there's no way you could put math on firm foundation. And then somehow we just forgot about this and we just move on, and it's okay. We just do math anyway. But this is a great drama. In fact, it's in great graphic novel form. Logic Comics. Highly recommend getting that graphic novel and checking it out. It's incredible. It's so well written. I don't think I understand the end of it, because it kind of comes down to this Greek play about Aeschylus. I never understood the ending. But it's a great history of all this craziness. So anyway, back before all that happened, Peano came up with these 5 axioms to make sense of what we're writing here from the point of view of set theory. We're gonna assume all that works. But what I do is I've asked you to read the 2 or 3 pages in the book on this. So you can just see how crazy and like, wow, people really thought about this in a different way. Like they broke this shit down in a way that we don't want to even think about it anymore. It's not my wheelhouse for sure. But from the 5th Peano axiom, so the 5th Peano axiom, from that we get what's called the principle of mathematical induction. And that's where we're going to principle of mathematical induction. And now this sounds better, right? Doesn't that feel better? I hope that sounds vaguely familiar, because everybody's had logic and proof, right? And we've all done induction proofs. When's the last time you did an induction proof? Camila, when's the last time you did that? Was it last semester?
I think we did one at some point last semester.
Okay, that's pretty good. I'm gonna ask everybody. Cecil, when was your last induction proof?
I think last semester as well for history of math.
Okay, that sounds pretty good. Olivia, same thing? Yeah, Cormac, same thing.
End of my first year with logic and proof.
Cool. How long ago was that? You've been here like 10
Last
years, 15
year, yeah.
years? Yeah, it's been a long time. Yeah. Cool. Feels like we've known each other for a while. I know it's less than 10 years. All right, so this is kind of where we're going to pick up. And the principle of mathematical induction is basically, we've got the idea. Let's just put the idea out. Let's do it in a pen that works. This pen hasn't just thrown yet. It's potentially good. So the idea is this. We have some statement P of n about the real numbers. It's not the real numbers, the natural numbers, about the natural numbers. And n is itself one of those natural numbers. So it's 1, 2, 3, 4, on up. Just nice counting numbers. All good. What do I mean by that? So what do I mean? P of n could be something like this, and it's literally a sentence with a variable in it. So every number of the form n times n plus 1 over 2 is even. And we say and we want that to be true for all. Let me put those symbols in there. Is this symbol, do I need to refresh what that means? What does that mean? For all. So this just means for every. This is called the universal quantifier. We're going to know these very well. Universal quantifier. And it just means for all. And you can say it that way, or you could say for every. And it's just saying that this is true for every natural number. In other words, i.e. when n equals 1, 2, 3, ... You pick a natural number, it's true for that. And actually, this is the wrong statement. I got a little crazy. I just meant this. Sorry, take out the divided by 2. Why would that be true? Just like, let's just start thinking mathematically. Why would that be true? We're not going to do an inductive proof on it, but why is that true? Just like, give me a heuristic. You're tutoring someone, and they're like, I don't see why this would be true. Help me, tutor. Explain to me why this is true. Oh my God, that is one creepy ass floor. Why is that true? How could we maybe attack this question? What would be some things we could do? Cormac, yeah.
You could assume that n is odd or even.
Okay. And we could even be more specific. We could like pick some ends and take a look at it, right? So in this kind of situation, I would actually just like pick some ends and go, well, what does that thing even look like? So let's look at let's start at the beginning. So here's going to be n. We're going to make n here. We'll make a little table. Here's n. Here's n times n plus 1. So when n is 1, this is 1 times 2. It's 2. When n is 2, this is 2 times 3. What does it mean to be even? Maybe we better make sure we understand that. A number n is even if what?
Divisible by 2.
Divisible by 2, evenly divisible by 2. Does that sound right? 2, 4, 6, 8, 10, 12. If it is divisible by 2. Cool. So, divisible by 2. Divisible by 2. Just keep going. 3. Divisible by 2. Yeah. What's the next one? Divisible by 2. What do you see happening here? Let me ask you this, Cormac, let's talk. Since you already answered, sorry. I'll lay off, yeah. You got an idea, a hypothesis?
It's always an even multiplied by an odd.
Yeah, that's it, exactly. So one of these, if this is even, then this is odd, but if this is even, then it's divisible by 2. If this is odd, then this is even. Notice how it's always odd and even, or even and odd. So one of these two numbers will always be even, so we could say, yeah, that's definitely true. And that's what we tell the person who asked us this, the person we're tutoring. Well, one of these two numbers is going to have to be even, because the real numbers, or the numbers go one, even, odd, even, odd, even, odd, even, odd. Yeah? Just warming up. Just warming up. So when I talk about a statement like this, a statement about the natural numbers could be something like this. It could also be something like this. Let's see, I've got an example that we're going to prove in just a minute. This is a weirder one that, let's say P of n could be this statement here. We will prove this together. 3 plus 11 plus dot 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 plus 8 times n minus 5 equals 4n squared minus n for all natural numbers n. So that's a statement, it's a claim that this is true. It's like kind of a formula, right? That if somebody gave me this weird ass sum over here, I could compute it quickly over here. So one of the first things you're going to want to do, the principle of induction says the first thing you better do is make sure this works for something. Like we did here. These are base cases. We want to take this statement and just be a scientist about it and go, well shit, is that even true for 1? So the first thing I'm going to do is get a base case. And the base case is it true? Is P of n true when n equals 1? So let's actually see, when n equals 1, what's this value right here? 3. It's just 3. It's literally only this 3 here. There's not much to add. So P of 1 looks like 3 on the left side. I'm I'm just plugging it into that. And then on the right side, I'm gonna put a little question mark here because I don't know yet. I haven't figured it out. But it doesn't take much to figure it out. It's 4 times 1 squared minus 4. That's 4 minus 1. That's 3. Yay. True. Cool. So now I know it's at least true for one thing. What's the rhythm here? What's the next number? 3 plus 11 plus what? If we were going up more. So this is n equals 2. When n equals 2, we've got 16 minus 5, that's 11. So this is the n equals 2 right here. What's the n equals 3 number? 19. What's the rhythm? Adding 8. So we're just adding 8 to move on up the chain. So the next one, once we see that, then we're like, it's 27. And this would actually correspond to the n equals 4 case right here. When n equals 4, I've got 4 times, wait, is that right? 1, 2, yeah. Did I add 19 and 8, right? Yeah, 27. When n equals 4, what do we got? Oh, 60, wait. Oh, that's the sum. Right. So when n equals 4, this is 32 minus 5, that's 27. Okay, cool. Got myself confused. Okay, so principle of mathematical induction says, step 1, check a base case. Check the lowest range of n this is supposed to be true for. Make sure it works. Just plug it in and show it. One of the things I'm really going to harp on you on in this class is communicating to me. And I want you to write sentences and words. And some of us have had battles about sentences and words. You'll get it back, and I'll just say, more words, please. Make beautiful words. The next step is the inductive step. And in this inductive step, this is the thing that comes from the 5th piano axiom. It says the following, that we now show that if P of n is true for some n, we don't know what, we're going to do it in arbitrary value, then P of n plus 1 is true. The next case is true. If the current case is true, the next case is true. And once we have that, here's P of n, and then we have P of n plus 1. If we have this implication here, let me write it like that. If I have this implication, then I've got this whole chain. So this thing, this is the base. From the inductive step, if I know P of 1 is true, and then this holds, if I can move from P of n to P of n plus 1, then P of 2 is true. I don't have to show that because I've shown it in general. This I established, this implication I've shown is true, and then from P of 2 I get P of 3, and then I get P of 4, and everything, it cascades from that principle. And this is how we show something's true for infinitely many things. We show this successor relationship. This is true and its successor is true. So, what do we do here? There's a lot of, you might have learned this in a lot of different ways, and I honestly will accept all sorts of different ways to show this. But the heart of what this next step is we're going to assume, we're going to write this out. Assume P of n is true. So what does that mean? i.e., now I'm going to write that out because I'm communicating to myself first and then hoping somebody can understand what I've written. 3 plus 11 plus, and you know what, let's put in the next one. We know that these are stepping by 8, so it was 19 plus blah, 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 plus 8n minus 5. That no matter what this n is, and the number of things that are here are going to be n. Notice there are n terms here. This was when n equals 1, when n equals 2, we got these two. When n equals 3, we got these 3. is equal to 4n squared minus n. So I just assume that. Now I'm kind of curious, since some of you have done induction more recently, maybe not a lot of it, or Christian's done it like a decade ago, so might not be as clear. Is anybody, what would you do next? So like what would you do next? So I'm assuming this is true. What do I need to show is true? What is it I need to show is true? Because I'm gonna write that out. Want to show what? WTS, want to show.
P of n plus 1 is true.
Yeah, let's write that out. And let's even write it out, right? Help your brain. Notation is technology. That's the only technology we got. I mean, ChatGPT could probably do this. But we don't need chat. We don't want to like give over the reins completely to our computer overlords. Not yet. And so what you need to do then is, what does this even look like? And so what I would suggest is we're going to take this P of n and we're going to tweak it. So to show this, start with P of n. Write that out and leave a little space. With some space. So I'm going to write out P of n again. I'm practicing it. I'm not going to use what I've already written. I'm going to copy that shit down again. 3 plus 11 plus 19 plus ... plus 8n minus 5. I'm going to leave space here because I'm going to plus something. So put in equals space. And then the other side is 4n squared minus n. I'm going to do that. Okay. What do I have to add here? What is the next thing going to look like? So we're going to add what to each side? What's the next term? If I want this to become P of n, to get P of n plus 1, sorry. How do I modify P of n to get P of n plus 1? Maybe you're not quite sure. Let me give you So here's P of 3. Let's just take a look. How do we move from P of 3 to P of 4? P of 3 looks like this. Wait, what did we start with? 3 plus 11 plus 19 equals, and then on this side I had 4 times 3 squared minus 3. What is P of 4? What do I add here? What's the next term? 27. So here I would add 27. And then here I would add 27. And that's still true because I did the same thing to both sides. But now this is now P of 4. I turned it into P of 4. And this side is my new formula. And that's where the work is going to come in. I'm going to have to modify this to look like the next formula. Let's actually do it right now. So let's see. This is going to be, what do we got here? What should this equal for P of 4? What should the right side be for P of 4? It should be 4 times 4 squared minus 4. Is this that? And now that's what I need to actually show. So I would do a bunch of algebra here and show that this side was, what do we got? 36 minus 3, 33. Did I do that right? No, that's, 36 minus 3, 33. Add 33 to that, that's 60. Is this 60? Yeah, it's 60. So what I would have to kind of do is manipulate this. Actually, I guess it just, I would just kind of like show that those two things are the same. It's gonna be a little trickier over here because we have n. So the key thing here is I'm gonna add the next term, which is 8 times n plus 1 minus 5. Sorry, I hope that didn't get confusing. Might have. But that's the next term. What's the one after this? Corbin.
Could you say, well, I guess you could say 8 times n plus 2 minus 5.
Exactly. And then it would be 8 times n plus 3 minus 5. Yeah, 100%. So I'm going to add this on. So I'm going to add 8 times n plus 1 minus 5 to each side. And I got to do it over here. Now the left side is exactly what I want. This is the left side of p of n plus 1. I need to show that this looks like the right-hand side of p of n plus 1. So I'm going to do a little scratch work. I'm going to do a little scratch work. Because the right side of p of n plus 1, so p of n plus 1, let's write it out. It's 3 plus, it was 3 plus 11 plus 19 plus blah, 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 plus 8n minus 5 plus 8n plus 1 minus 5. And this would equal, now I'm just going to replace this n with n plus 1. So it's 4 times n plus 1 squared minus n plus 1. I need to convince myself that this looks like this. How could we do that? What would you do? And there's lots of ways. I would like, give me some algebra routes. Could actually maybe take a minute. Take a minute, do the algebra. Expand this out. Expand this out and convince yourself those are the same thing. And record your algebra. Try to like be meticulous in your steps so that you know what you're doing. That's the first step to convincing someone else you do. Get the first homework set up here. Pretty good. All right. Let's make sure we all see that in your own way. And then I want to show you how to put them together to make people think you're a math genius. Looking like a math genius is a lot of prep on the side. It's just like a magician, just like magic trick. Getting there, getting there. Yeah.
Close, yeah.
It's still slow, too
It's
slow.
fun though. It's what's good.
Yeah, 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 yeah.
Do you want to show from the right side?
Yeah, essentially, yeah, exactly. And then we just want a nice flow. How you feeling about this?
Did you forget your notebook today? Or you just got something? That's it.
No. Do you need some paper?
I have about enough.
Okay, good, good.
Okay, I'm ready.
It's okay, no, I see you right. It's all good. I'm not judging. No judgment. I forgot a major thing for my next class, so I get it. So I'm going to just kind of slowly put these together. This, I just like took this and expanded it out into a polynomial. I just like literally just broke this down. What does this simplify into? And then over here, I wrote what it should look like and broke that down. And the good news, they're the same. But now what I'm going to do is look crafty. See, I've got this here and I've got this here. I'm going to write these steps backwards. And then I'm going to say something shifty like this. Notice that this equals this. So this equals 4n squared plus 8n plus 4 minus n minus 1, which of course clearly equals 4 times n squared plus 2n plus 1 minus quantity n plus 1. See how I'm just writing that backwards? And it looks like I saw this. And so then this is just 4 times n plus 1 squared minus n plus 1. And that is literally the side I needed to have this look like. And I got there. But it took a little hocus pocus on the side. So we've shown this, therefore, so I'm using the triple dot, therefore, P of n plus 1 is true. Remember how this flowed? I assumed P of n is true, so I showed P of n implies P of n plus 1, I'm good. And then I summarized this all, last line, by the principle of mathematical induction, the result follows. Something like that. You know, use your own words, but you want to sum it up and say, I just used induction, and I did it. It worked. Does this sound okay? Yeah? Let me do an example for you, another one, real quick. Let's see, yeah, we got time. Let me do one more example for you, just so you have it. Is there any questions before I erase? Anybody need time on this? I'll erase the right side first. Oh, and there was this homework assignment up here. And I just erased. So let's shoot for next Wednesday, even, by the end of the day or something like that. I kind of prefer everything in hard copy, please. Also include problem statements as well. 3.6a. So just these 3 problems by next Wednesday. And again, please include the problem statements. They're not copious, they're not overwhelming in any way, shape, or form. Next Wednesday. And then my goal would be to get those back. You would have those back the Wednesday when we come back, and then you can do any tweaks you need. So my goal is to get shit back to you fast. That's also kind of the advantage of this grading system, that I should be able to get things back to you very quickly. Okay, let me do another induction example for us. So, show, this one's kind of cool. Show that for any real number x, so x is a real number, sine, the absolute value of sine of n times x is less than or equal to n times the sine of x. I never knew that result. I think that's a really cool result. I think that's pretty crazy. For all natural numbers n. Let's think about what that means, just real quick. Okay. This is, what the heck does that mean? That means that if I take sine of nx and I graph it out, and here's x, what's the period of sine of nx? I heard a gasped n. What's that, Cormac?
Is it n?
It is related to n. What's the period of just sine? What? How much?
Pi over 2.
That is related to the period. That is a fraction of the period.
Is it 2 pi?
It is 2 pi. It is 2 pi. Let's sketch out a normal sine graph first. Why don't we just real quick? Normal sine graph looks like this. 2 pi, what is the max amplitude, minimum amplitude? Yes, you are, you got it. Lives in that little box right there. What's right in the middle? Hey, all right. And then here's that pi over 2, Cormac, right there. There we go. Yeah, it's about a quarter of the way through, and then that's 3 pi over 2 right there. So that's what a sine looks like for any x, and then of course this continues on forevermore. How does that relate to sine of nx? Well, let's think about sine of nx. When the nx is equal to 2 pi, in other words, when this quantity here achieves the value 2 pi, we've hit a period. When this n times x hits 2 pi, that happens at 2 pi over n. So that's the period of this thing. It's contracted. It's squished. It happens faster than the other one. So if this is 2 pi over n, this is sine of nx. Minus 1. It still has the same output. We haven't scaled the output. We've only scaled the input. And then it kind of looks like this. And then this would be pi over n in the middle, because it's half of that, and blah, blah, blah. So it's a scrunched up sine wave. And depending on how the bigger n gets, the more scrunched it gets. When n is 100, it's super crazy. It's a lot. There's 100 periods happening in this space right here. So what this is saying is that no matter what x value I pick down here, so if I pick this x and get that sine out, that sine, the absolute value, the output, this length right here, is less than or equal to n times the value of that same x up here. So we've got this is sine of x, and this is sine of nx right here. It's telling me that this thing here has an upper bound of n multiples of this height right here. For what that's worth. I don't know what use this is, but I thought it was kind of cool. So how do I prove this? Proceed by induction. So proof. Proceed by induction. What's the first thing I need to do for induction? Yes, ma'am, base case. So I write that, I say base case. And we're using the natural, so we're gonna start at the bottom level, n equals 1. And we're gonna say that sometimes it helps to label that, that's P of n. That's our statement that this thing is true. The x, we're gonna assume the x is fixed already when we enter here. That no matter what this x is, this holds true for every 1, 2, 3, 4, blah, blah. So the base case, what does P of 1 look like? Olivia, what's P of 1 look like?
Would it just be like sine of x equals sine of x?
Yes, ma'am. Yeah, so here's the left side, and we're gonna write it out. 1 times sine of x absolute value. And yeah, because we got the equals here, so yeah, that's true. They're literally equal at that point. Because sine of x is sine of x. So cool. Base case, really simple and chill. Amazingly, now we just have to like go to the inductive step. So this is the base case. Now let's go to the inductive step. Inductive step is assume P of n is true. So that means I'm assuming that statement up there. We've already got it written. I'm not going to write it again. What I need to do is now show that P of n plus 1 is true. I'm going to maybe proceed in a slightly different way. Let's see, so I'm going to get my goal set up so I know what I'm going for. What does P of n plus 1 look like? Could you write that out? Because we want to know our goal. Take a minute, write out P of n plus 1. What is it we're shooting for? What is it we want to show? Let's just make sure we agree. And then I do want to show you there's another way to proceed. This one's going to look a little more like we're going to start with this left side, use a trig identity, and show that it's bounded above by this side as long as this holds true right here. That's going to be our plan. So another way to proceed. All good? Good. Okay, awesome. So notice, that's just a great math word. It just, it helps you move into anything. Notice that absolute value of sine of n plus 1 x equals absolute value of sine of n x plus x. Does anybody happen to recall that sine of alpha plus beta equals what?
Sine of alpha plus sine of beta?
If close, I like this part, and I like this, actually, it's close. It's if there's a product here plus a product here.
Oh, is it plus I sine?
Ooh, I like that you're getting that fancy, but
Or
no
sine.
eyes.
Oh, no I. I don't know.
It's okay, I appreciate it. That would help. That. And you could have looked that up. If I don't know that, they shouldn't be paying me. But you're paying. You're paying for me to be here. So thanks. Appreciate it. For how long, I don't know. We'll see how Regis goes. They were almost talking about getting rid of the math major. Can you believe that? Isn't that fucking idiotic? Unbelievable. Like that will save money. That's right. If you're watching this, administrator, I think your decisions are fucking idiotic. All right, so we've got this. So this is going to be my alpha. This is my beta. Luckily, you didn't make that decision, so I'm just kidding. So this becomes equal to absolute value of sine of nx cosine of x plus sine of beta, so that's sine of x, cosine of nx.
And I just realized we're gonna use a result we haven't talked about yet, but it's okay. Maybe it's a good way to talk about it.
Does this all seem reasonable so far? All I did was use the trig identity. But now what's kind of cool is I'm seeing a plus appear on the outside here, which might help me get something more like a plus outside of the absolute value, outside of the of x part. So what I'm gonna say is that this is less than or equal to, and this is the part we haven't talked about, this is the triangle inequality. And I'm sorry. But the triangle inequality says this, that if I have something plus something else, it's less than or equal, in absolute value, it's less than or equal to the sum of the absolute values. So put whatever you want in there. This is honestly going to be one of the most important results this semester, so we will talk about it. So the triangle inequality says absolute value of a sum is less than or equal to the sum of the absolute values. And you can kind of think, this actually kind of makes sense, because when they're inside here, they might cancel each other out. One might be positive, one might be negative, so they have a chance to get smaller. But out here, I'm only adding positive values. So it kind of makes some intuitive sense. So what I'm going to do is break this apart into absolute value of that plus the absolute value of that, and that's less than or equal all of a sudden. And that's kind of cool, because look at what we're trying to show. All right, we got one more big move, and we're just about done. Let's use another, this is kind of just a basic property of absolute values, but if I have the absolute value of something times something else, that's literally just the product of their absolute values. So you can kind of distribute the absolute values, right? Like this, if this turns out to be a negative number, it's still going to have the same magnitude as both these positive numbers multiplied together. Negative 2 times 3, absolute value is still 6, no matter how I do it. So I'm going to break these apart. So this is equal to absolute value of sine of nx times cosine of x plus absolute value sine of x times absolute value cosine of nx. And I think since we reviewed cosine, we probably ought to review sine. Cosine of x. What does cosine of x live between on its outputs? Yeah, exactly. 1 and negative 1, and it looks like that. Oh, woo, not bad. Looks like that. Cosine of nx still has an output from -1 to 1. It's just this period here is a little lower. It's 2 pi over n. But cosine of nx is less than or equal to 1 in its output. That's all I'm saying, that the output of cosine of nx, so cosine of x is less than or equal to 1, cosine of nx is less than or equal to 1, no matter what n is, or all natural n. They live in this strip, no matter what. So that means this thing here is less than or equal to 1. This thing here is less than or equal to 1. We're just about done. Because that means this side is less than or equal to sine of nx times 1, I'm not going to write it, plus absolute value sine of x times 1, not going to write it, yeah, got scared for a second, everything's okay. Whew. I haven't used the inductive hypothesis yet. Remember what our inductive hypothesis was? Recall, we assumed this. We assumed that was true. Do you see? Take a minute. Let your brain hurt. You need to eat a snack. Can you see how we can move from here? Let me give you a hint. If I can get this, if I can show that this is less than or equal to this, then I have what I want. So take the inductive hypothesis. Let me put it here so you can see everything together. You know already how can you put this together with this statement to get this? Take a minute. You're stuck. Take this and use this statement to move it forward. This is less than or equal to something. Anybody have a sense of where to move? What do you think, Cormac?
I was gonna say, since it was like something like, since you know sine of nx is less than n sine of x, then it can never be greater than like n plus 1 times sine of x. Is that somewhere?
You're almost there. We can literally just say that this piece right here, you're thinking the right direction for sure. This piece here is less than or equal to this. So like this thing, this right here, this thing is bigger than or equal to this thing. But I still have this chunk here. So this piece alone is less than or equal to this piece. So look, I'm taking this statement here, this sum, and I'm replacing this with something that's bigger than or equal to it. So the whole sum becomes bigger than or equal to it. Check that out. Look at that statement. Try to make that make sense, because it's a hair away from what we want. Because the next statement is, I'm just going to factor the sine of x out. And that's literally this. Now this isn't something I would expect, like this is hard. And we're just warming up. So like if you're like, shit, I don't remember sine, don't worry about it, you don't need to know sine. We're gonna warm up, we're gonna practice all this stuff together. We're here to learn, improve. Your problem is not this hard, I swear. I expect almost no one to do trig anymore, so it just doesn't happen. Feels like you need an abacus to do trig or something. Can I answer any questions on that at all? Cool. Let's kind of push forward just a little bit. We got some time left. So that's enough induction. You've got one induction problem, I think. And it's a simple one. Like the first one I did, it's like that. It's not like this, so I promise. Maybe if you can, just take a look, read through the problems before Wednesday. That would be great. Like if you do that, then you're fulfilling my dreams, making me super happy. Let's build some more numbers. We don't have enough numbers yet. Because we just got these guys, the natural numbers. Can't even talk about half of something, right? We can't talk about negatives yet. Well, hell, we don't even have the most important number of all, 0, in there. When this number came along, people lost their shit. But mostly in the West. I think the oldest one is on a Hindu temple somewhere. Is that right? Did we have? I feel like I've had this conversation with at least a couple folks in here. Somebody saw it on a Hindu temple, like a 0 written somewhere. So but the Hindus, they understood. They had like ideas of infinity and big things long before the West did. Anyway, so if you take 0 and you add in subtraction, you want to be able to take 1 minus 2, and you start to get -1. So the next number system up that allows us to incorporate a 0 and subtraction is the integers. So that's all the naturals, including 0, and then the negatives thereof. Let's just talk about a couple little things here. This system here is closed under addition. If you take any 2 of these and you add them together, you land back in there. It's not closed under subtraction because 3 minus 3 is 0. It's not in there. This is closed under addition and subtraction. So now we're kind of getting things a little bit better. Does that make sense when I say closed under? Yeah, cool. But this isn't. This is closed under multiplication as well. Take any 2 of these, they're back in there. So it's closed under plus, minus, and times. Cool. But it's not closed under division because there's fractions. So if we want a number system, the next one up that allows us to divide, then we have to move to the rationals. So this, of course, is the integers. And then the rationals, you're going to get to know these guys more than you've ever known them. The rational numbers are all ratios of integers. So all A over B things, where A and B are integers. And what do I got to make sure of? B isn't 0. I just don't want to divide by 0. Because if you can divide by 0, then lots and lots of bad things happen. If you can divide by 0, prove 1 equals 2, because if you have 0 equals 0, 0 times 1 is 0 times 2, and as soon as you can divide by 0, then all sorts of hell breaks loose, right? So we don't, that's not good. So we've got those guys. Now, this is a lot of numbers. In fact, if we start thinking about the real number line, and we start trying to plot out where all these rationals are, we might start just putting dots at like a half and at 0. And then we start to realize this is a very challenging problem to put a dot where every rational is. In fact, it's impossible. There's infinitely many of these. But these aren't all of the real numbers. So not every real number is rational. What do we call the ones that are not rational?
Irrational.
Irrationals, yeah, that's good. Give me an example of an irrational number. That's a good one. Give me another one. Everybody give me one. Oh, you got it, yeah. The sooner you answer, the better you are.
Square root of 7.
Cecil, give me one.
0.6 repeated.
Oh, I love that you said that. That is not, but hell, that's a good one. Let's put that over here. It sure seems like it would be. And it's very demonically wonderful. I like it, but it turns out to be irrational. I'll prove that to you. Give me another one.
Square root of 3.
There you go. Beauty. Square root of 3. Cormac.
Square root of 2.
There you go. Holy shit. I got 2. Awesome. Cool. Now, we are not sure. So what this means is that these are irrationals. They can't be written as a fraction, as a over b, where a and b are integers. They cannot be written that way. We're not out of time. It's kind of the end of the class today. So we're gonna pick up here. But if you read ahead a little bit, you'll feel so much better. I would honestly rather have you read this part than the piano axioms. So if you're gonna read anything between today and Wednesday, start on page 6 and just read, maybe read up to page 10, if you could, page 6 to 10. That would be the best thing you could do possibly for Wednesday. And just look at the homework problem, just look at it. All right, thank you, my friends. And we might extend the homework a little bit. What I'm kind of thinking is I'd like you to just try it, and since you can keep retrying things, you know, it doesn't have to be perfect on the first pass. I think that's probably our best. That might be better. Let's just stick to Wednesday. Give me something. That's all I ask. Thank you, friends. It's good seeing you all again. Oh, and then I'll get back on this, Cecil. And you'll probably actually see it in the book. But Cecil, actually, I think I can answer your question. Right? Yeah. Oh my, okay.
Are all of your classes in
The next one, this one and the next one, and then this afternoon we're in 4th floor of Clark.
Yeah, no one Loyola.
None in Loyola, yeah.
Bizarre.
It is weird, I don't like it either.
That's why I was like, because I thought it was in Loyola. And I was like, wait a minute.
Were they genuinely thinking of ditching the math major?
Uh-huh.
That's ridiculous.
It's so stupid, and I don't understand how they think that saves any